Alright guys, today we're going to talk about times when acceleration is a function of velocity. And so typically when we have acceleration as a function of velocity, it's some type of problem involving a drag or an air resistance, where the faster and faster we go, the more and more we have a force that's impeding our motion. And so that's either going to reduce our forward acceleration or actually create a reverse acceleration which slows us down. So the first example we're going to talk about is, let's say that we are coasting to a stop with some positive V0. So an example of a time this might happen, let's say you took your car out onto the interstate and there were no other cars out there, so this wasn't a dangerous thing to do, and you got it up to some initial speed or velocity, say like 60 miles per hour, and you just let off the gas. So you didn't actually hit the brake, you just let off the gas. And so of course, because of air resistance, your car is going to start to slow down. But what happens is the slower and slower it gets, the less and less air resistance you have. So actually what happens is, as it slows down, the rate at which it slows down decreases. And so over time, as our velocity approaches zero, our acceleration approaches zero, and mathematically neither of them ever really do. So if we have a problem like that, what we end up with is we have acceleration as a function of velocity, and our acceleration will be negative. If we have a positive velocity, then the acceleration is in the opposite direction. And so as we continue going, our speed gets lower and lower, and so the acceleration actually gets lower and lower. So the slower we get, the less we slow down per unit of time. Now, if you remember, acceleration is actually the derivative of velocity with respect to time. And so we can write that dv over dt equals negative kv. And so what we've just written is what's called a differential equation. And by solving this differential equation, we can actually develop an equation for velocity as a function of time. And the first thing we have to do for that is do what we call separating the variables. And by separating the variables, what I mean is we need to get all the velocity stuff on one side of the equation and all of the time stuff on the other side of the equation. Now there's usually more than one way to do that. The easiest way to do it for this particular problem is to say that dv divided by v equals negative k dt. So as you can see, now I have all my velocities on the left side and all my t's on the right side. Alright, so I've rewritten the equation here, but instead of writing dv over v, I just wrote 1 over v dv. And then on the right hand side we've got negative k dt. And now that we've separated our variables, what we actually have to do is integrate each side. And as we talked about earlier, the integral of 1 over u is always 1 over the derivative of u times ln of u. So in this case, it's going to be just ln of v plus c. And then on the right hand side, we're going to have negative kt plus c. So what we see now is we have two arbitrary constants, and we don't know the value of either one. So let's say hypothetically that this one had a value of 2 and this one had a value of 8. There's no point in having both of them. We could just say this one's 6 instead. So what we do is when we have an arbitrary constant on each side, just get rid of one of them. So now we just have ln of v equals negative kt plus c. And we want to solve this for velocity, so we're going to do e to the power of each side, and that's going to give me v on the left hand side, and then on the right hand side this is going to give me e to the negative kt plus c, which hopefully you remember from your math classes is the same thing as ce to the negative kt. Alright, so now we have that our velocity equals ce to the negative kt. So we can see here, if we plug in a time of 0, we'll get v equals ce to the 0 power. And of course anything to the 0 power is 1, so really then just v equals c. Now when we plug in t equals 0, then that v we've actually plugged in is v naught. So what we've really figured out here then is that the c in this equation is our initial velocity. And so the final equation we have here is that v equals v naught e to the negative kt. Alright, so let's say we have an example with a equals negative 0.4 v, then dv over dt equals negative 0.4 v, and 1 over v dv equals negative 0.4 dt. And then I'm going to integrate both sides and go and get my equation for velocity as a function of time. So we end up getting that v equals v naught e to the negative 0.4 t, which is what we'd expect looking at what we did just a minute ago. And let's also say we know that the initial velocity was 25 meters per second. So maybe you had your car cruising along at 25 meters per second and you took your foot off the gas or put the car in neutral. Then what we could say is that the velocity of your car as a function of time is going to be 25e to the negative 0.4 t. And so what we'll see is that over time the car will get slower and slower and slower. And basically what ends up happening is that as your time approaches infinity, the velocity is going to approach 0. Mathematically, it would technically never reach it. So let's look at what happens if we want to now know position or acceleration as a function of time. So we now know that v equals 25e to the negative 0.4 t, and let's say we started at a position of 0 meters and we wanted to know our position as a function of time. Well, of course, position always equals the integral of velocity with respect to time. So that's going to be the integral of 25e to the negative 0.4 t with respect to time. And so if I integrate that equation right there, I'm going to get 1 over negative 0.4 times 25 times e to the negative 0.4 t plus c, which works out to negative 62.5 e to the negative 0.4 t plus c. So since we said that x naught was going to equal 0 meters, I'm going to plug in 0 for x, I'm going to plug in 0 for t, and I'm going to solve for c. So 0 equals negative 62.5 times e to the 0 power plus c. And since anything to the 0 power equals 1, then I get that c must equal 62.5. So now I have my position as a function of time as 62.5 minus 62.5 e to the negative 0.4 t. And I usually leave it that way, but technically it is more simplified if you write it 62.5 times 1 minus e to the negative 0.4 t. But that equation to me is harder to use, so I typically don't simplify it like that. If we want to know our acceleration as a function of time, we just have to remember that that's the derivative of velocity with respect to time. So if I take the derivative of 25e to the negative 0.4 t, then what I'm going to get for that is negative 0.4 times 25 times e to the negative 0.4 t. And if I work out negative 0.4 times 25, that's just negative 10. So I get negative 10 e to the negative 0.4 t. And so we'll see there that as the time approaches infinity, the acceleration also approaches zero. If you look at the position versus time equation, as the time approaches infinity, the position is going to approach 62.5. So this object would actually keep approaching a total displacement of 62.5 meters, but never reach it.